Hello everyone. Today we are going to start a new chapter and last chapter of course for this course, light sources and photodetectors for integrated photonics. First we will be discussing about integrated photonic light sources. You know there are various type of light sources available, but we will be discussing something suitable, technologically suitable for integrated photonics or photonic integrated circuits. As we say integrated photonics or photonic integrated circuits. So, waveguide is the fundamental building block. So, I think we have to concentrate more on light sources or laser sources which is designed based on waveguide. So, I will be discussing about waveguide laser fundamentals. And then as you know semiconductor laser diode, that means light emitting diode or laser diode, these are actually the most efficient light sources. And how those type of semiconductor laser diodes can be integrated, that is the challenge for the photonic integrated circuit, of course that will be discussed in this course. But before going into that in detail, we will be just discussing about the working principle of a semiconductor laser diodes. Okay. So, let us move on to the waveguide laser fundamentals. So, it is not much different from laser fundamentals, the laser working principle. Just we will be using, instead of a free running electromagnetic wave or light source, light energy, we will be considering that a guided mode, that is it. So, we start with a waveguide Fabry-Perot cavity. As it is shown here, a waveguide here, this is the top view of the waveguide. It can be a single mode, that means the confinement like this, the field distribution will be like this, laterally it will be confined and vertically it will be confined, but it will be allowed to propagate in one direction. But with a certain length you can have some kind of mirror here. So, these mirrors here and these two mirrors. So, that means the waveguide both end facets you can deposit a mirror, and or you can think of that the waveguide, instead of this mirror can be a DVR mirror. So, it can be a DVR2 distributed Bragg reflector 2, and this can be also this side you can extend and you can have a mirror DVR2 DVR1 sorry. Okay. So, instead of just standard dielectric mirror deposition, you can think of distributed Bragg reflector integrated into the waveguide, that will give you selective reflectivity for certain bandwidth. So, that can also be considered. We have discussed earlier already DBR cavity, right. So, you can think of that type of cavity as well, but for understanding purpose we just consider a lumped mirror here and giving you reflectivity R1, small r1, small r2. The small r1 we mean, that means the reflection coefficient, amplitude reflection coefficient. Okay. Normally intensity reflection coefficient I can write like this, R1, R1 star, and R2, this one R2 star. That would be your normally called reflectivity of mirror 1 and mirror 2, but R1, R2, that would be simply amplitude deflection coefficient of the guided mode. And then we know that this Fabry-Perot cavity standard resonance condition we discussed earlier also, just reproduced here, that phase because of the phase acquired because of the round trip travel. Okay. So, one round trip, if beta is the propagation constant defined by beta equal to omega y c, n effective is the effective index of the guided mode, can be also written in terms of lambda 2 pi by lambda n effective. This n effective can be also lambda dependent or frequency dependent. And then this is the phase constant for a given lambda, and then round trip total phase, and this phi m1 and phi m2 if at all any phase being introduced by mirror 1 and mirror 2 respectively. So, for one round trip it goes here, travels here, beta L phase, comes back with a reflection and phase phi m1 and again beta L phase and again gives you phi m2. Then one round trip completes. That means, one round trip means double pass and then double reflection from mirror 2 and mirror 1 respectively. So, this would be phi m1, this would be phi m2. I am sorry for that. So, if this round trip phase is equal to 2 pi times integer m equal to 1, 2, 3 and so on, then we can say that that particular omega or that lambda is resonant to the cavity. So, electromagnetic wave or guided mode associated with that lambda, that will see some kind of energy storage. It will be seeing some resonances. Okay. So, that thing for that discussion to proceed, what we consider here, just for simplification, phi m1 and phi m2, most of the time if it is dielectric material, they can be 0, they can be assumed to be 0, but if it is a DBR, for example, you can have this phi m and phi m2 both. If it is DBR2, for example, instead of this mirror replaced by DBR2 and this mirror replaced by DBR1, as you know, reflectivity from a distributed Bragg reflection reflector integrated with a waveguide, that can be frequency dependent as well as that can be frequency, every frequency that can have different phases also. So, that need to be considered. For the moment we are discussing they are 0. So, in that case I can just consider beta equal to omega by c, and then always omega we can write like 2 pi by 2 pi nu. Omega is the angular frequency and nu is the linear frequency. So, in terms of resonance frequencies, we can express that nu m equal to m c over 2 n effective L. L is the total length of the cavity. Okay. So, now again we know that nu lambda equal to c, velocity of light, they are related. So, we can just convert nu into lambda, then we can find this one. So, m is the integer. So, depending on the length, you can find out to have, for example, if you want to have a resonance wavelength around 1550 nanometer and for a given length say equal to 1 millimeter, and n effective for silicon waveguide, for example, if I just consider that is around 2.8 or so, then you can find what is the value of m required. So, that is the integer value that would be considered as a order of the longitudinal mode. M is actually counting the order of the longitudinal mode. M equal to 1, then first order longitudinal mode, m equal to 2 second order longitudinal modes, because we are considering resonance in the round trip path. So, it is called longitudinal modes, and those longitudinal modes actually if you want to represent or if you want to see as a function of frequency, here x axis is the frequency and y axis is your transmission. Transmission if you see, then we can say that a certain range of frequencies, if you consider this equation, n effective and L if you are considering suppose constant, for example, it's not does not depends on effective index does not depends on frequency, for example, if you consider. So, in that case that regularly you will be getting this one, for example, assigned as a nu m or lambda m. M can be say 1000 depending on your wavelength or your effective index and length, and then you can have nu m minus 1. Whenever m equal to m minus 1, then you can have another frequency, because frequency will be reduced, m plus 1 frequency will be increased, corresponding lambda m plus 1, lambda m minus 1 you can find like that. And we have also shown that such longitudinal resonance frequencies, they are spaced by a term called free spectral range. Free spectral range FSR, and FSR equal to delta nu here represented, that means the separation between successive resonance frequencies, and they can be expressed by C over 2 NGL, where Ng is the group index. We have shown earlier that is nothing but, if it is in terms of lambda, N effective is given, then you can write like this. Otherwise, if N effective is given in terms of frequency, then you can write omega d n effective by d omega. So, this is the group index. So, depending on the group index, that means how much is the dispersion in the waveguide involved, that actually decides the separation between longitudinal frequencies. So, this is all what we have discussed about Fabry-Perot cavity, and that has been discussed earlier of course in this course, but here we have just repeated the same discussion just to understand how a Fabry-Perot laser works. Okay. Now, let us see. Suppose in this waveguide you have somehow some energy supply is there, you have certain kind of pump, then such that in this waveguide it becomes active. When active means any signal, electromagnetic wave signal with a certain frequency, that can get some kind of, that can see some kind of gain amplification. Okay. So, if that pump is given, some energy is given such that your signal propagating through this electromagnetic signal propagating through the waveguide will see some kind of gain. If that gain coefficient is given by G, and that can be frequency dependent, and I is the intensity, that is also frequency dependent and position dependent, that as it propagates it will see some kind of gain, it will be increasing. So, we can write down that equation, the evolution of intensity or power, I can be written as a power also. So, a cross section of the waveguide, if you multiply, you just multiply cross section of the waveguide left hand side and right hand side, that will give you some power evolution equation for power evolution. So, you can see that this rate of change of or differential change of intensity shown by here, that must be proportional to the intensity and gain coefficient, and of course, you should count also the loss parameter of the waveguide. Remember that this G and alpha, this is actually loss parameter of the power loss coefficient. Suppose if you have a power at z, if you want to define from P 0 e to the power minus alpha z. So, that this is actually power loss coefficient. Earlier you remember that alpha we normally consider, alpha is the loss coefficient for the amplitude. So, if alpha is the loss coefficient for the power, so amplitude loss coefficient will be alpha by 2, because you know power is nothing but power or intensity is nothing but E star. So, if electric field loss coefficient, if you are considering, that is alpha by 2, then E star becomes alpha. So, intensity loss coefficient can be alpha. Okay. So, if it is that, so we can write down the intensity evolution along the waveguide. Suppose we are considering this is z direction, we can write like this. Okay. And this gain curve, as I mentioned, depending on the pump, depending on the material you are using, that is actually how is this active waveguide, you are defining what type of material, all these type of things actually involves. Mostly in physics, if you see, that actually involves what is the energy band diagram of the material used for the waveguide under consideration, and also how is the population inversion is created. Population inversion is very well known, very much known in laser physics. I will be discussing in terms of semiconductor here. Okay. So, that can have frequency dependent, this G can be frequency dependent, but alpha we are considering it that it may be flat for all frequencies under consideration. So, here it is shown that gain curve, these are the longitudinal frequencies of the cavity we have shown earlier in the previous slide. These are the longitudinal frequency and their separation delta nu equal to C by N G L as we have given, and you say this is the gain curve. So, that means suppose this is your new M, for example, earlier we have shown. So, we are considering that okay, this gain is some material is such that it is actually giving maximum gain around the mth resonance frequency, and it may be Gaussian type or any type of, it can be different type of shape, it can be something like this type of shape also. Okay. So, it will have some kind of bandwidth and it will have some kind of distribution, gain distribution, frequency dependent gain distribution. Here this pink color is shown as a gain curve, as a representative one. Typically it will be maximum somewhere and both side lower frequency and higher frequency side it will be dropping, that is the typical gain curve. But the nature can be Gaussian, that can be some asymmetric Gaussian, that can be something completely different function, that may not be possible to represent with a function or so. Now, let us define a certain thing called threshold condition. So, normally if you know, we want to discuss about laser, waveguide laser. Laser you know that is actually light amplification by stimulated emission of radiation, laser, light amplification by stimulated emission of radiation. Okay. So, that means light will be amplified because of the pump, because of the gain, and that gain actually comes with a particular term called stimulated emission. So, emission will happen, that will be stimulated, that will be triggered, that will be initiated by some means, that is called, for example, if you have a certain photon with certain frequencies propagating, and if it is the medium is such that this one photon actually help to emit another photon also from the material of same property of that initial photon, whatever the property associated for the initial photon, then it will be called stimulated. That is actually quantum mechanical process, or maybe classically you can explain using a dipole oscillation, etc. We are not going into that detail, but stimulated emission required. So, that stimulated emission actually gives you gain, but that gain, as you see that in this equation right hand side you have one positive term, another negative term. So, that means you can imagine that to get a net gain you need to have G, certain value of G overcoming the losses. This loss in this case, here we are considering that the propagation of the electromagnetic wave in a gain medium, but whenever you have a mirror, that means after traveling a L length it gives some kind of reflection into the cavity, that means giving some kind of positive feedback, and coming back again this mirror also gives some kind of positive feedback. That means when it is propagating, getting gain everything fine, then when reaching to the mirror, then entirely will not be reflected, part of that reflected, some of them will be lost this side. So, here also some of them, every round trip it will be lost this side a little bit, this side a little bit, you can imagine like that. Okay. But thing is that pump is continuously supplying energy. So, every time it goes, it amplifies little bit loose and little bit coming back and comes back again. So, this every round trip it goes on and on. So, it will go for amplification and so on. At every round trip you will get some kind of losses also, but there should be some kind of steady state condition for a given pump here, for example supply. So, this can be bias or whatever. Okay. So, but we would like to know that when this laser to emit, is there any threshold value for the pump or not, or for the gain, is whether you need a certain threshold gain to have a laser emission or not. Significant amount of laser light emission will be there with a good property, so called coherent property, etc. For that purpose, whether you need a threshold gain or not, that thing we will be trying to understand now. If there is existing at all or not, or just keep on pumping, you will keep on getting some laser source or not. So, let us see. Now, you see field gain in one round trip. Suppose you have your initially your field was, you are considering at any instant of time, the E naught is the field. Now, after one pass, this field, when it goes to its travel L length, this field will be evolved with a phase of this one and with a gain of field gain is G by 2 times L, and it will evolve with a loss of minus alpha by 2 L. So, after one pass it gets like this, and then after reaching here it sees some kind of reflection coefficient R 2. Then what happens? It comes back again, it travels and then comes back another L length. Then this again it will be multiplied by e to the power minus j beta L, and again it will get some additional gain. This is phase gain, this is just amplitude gain normally, and then again you will be getting some kind of loss one pass. After coming back here, again it will see reflection. So, that means this we call it as a E 1. So, we started with E naught, one round trip it gives you E 1. So, if I just take E 1 by E naught, that is what this comes like this expression. Okay. You just simplify this thing, then you will be getting this thing. Remember that G and alpha is considered gain coefficient and loss coefficient for the intensity of the intensity travelled through the waveguide. Right. Now, what you see, intensity or power gain in one round trip. So, that means intensity of power gain, when I am talking about gain, that means E naught by E 1, that is amplitude gain, and intensity gain will be E 1 E naught star, that will be intensity or power gain proportional to that one. Then what you will see? You see complex conjugate and multiply. So, this thing can be phase part can be e to the power j beta delta L, that will be cancelled, R 1 star will become R 1, R 2 star will become R 2, and this will be multiplied by 2 times complex conjugate. So, 2 will go 2 L G minus alpha. So, this will be the intensity or power gain in one round trip. Now, suppose this gain is 1, that means after one round trip you are actually reproducing that energy, whatever energy is being lost or gain after one round trip, it is just 1. So, that means you have nothing lost, you are losing nothing or you are gaining nothing. So, that type of situation, that type of gain, when you are that type of condition whenever achieving, that can be achieved for a given alpha if you supply a certain G, and that G value if you are just representing as G threshold, just here you put G threshold, for G equal to G threshold you can get this one equal to 1, that is what we have written here. So, that means G threshold is the definition of the gain or the gain coefficient required for which a round trip gain will be 1. Gain G threshold is the gain coefficient you are activating after supplying pump into the waveguide, laser active waveguide. Then one round trip the intensity or power gain will be just 1, that is, remember that there is a power gain, but G threshold we are considering threshold gain coefficient. So, that gain coefficient can be controlled, the value of the gain coefficient can be controlled with the pump power level pump here. So, it is actually it can be controlled basically externally depending on your pump supply. So, now from here you can find out G threshold equal to this expression. and normally this alpha we know that is actually your loss coefficient, right, and this one we can think of this thing, this is the loss because of the two mirrors, and you are dividing it by 2L. That means that division 2L means that means your mirror loss, which is actually lumped losses here and here happening. When propagation, when the signal goes here at this lumped point at a one particular spot where you are losing something and then comes back, and again because of the mirror here you are losing not completely reflected. So, that loss is this one total loss for two reflection, okay, and that has been divided by 2L, meaning you have distributed that, you are just considering that one as a per unit length, whatever the mirror, you are just distributing the mirror loss into the entire cavity. So, in that case that we are writing like the alpha mirror loss, distributed mirror loss. That means, instead of just lumped loss, we are considering that per unit length how much loss coefficient is there. So, this is actual alpha total. That means, that G threshold, that means gain coefficient must be exactly equal to the right alpha coefficient, the loss coefficient, total loss coefficient. One is the waveguide loss coefficient, contribution coming from waveguide loss coefficient, and another is the mirror loss coefficient. Then that time you can say that one round trip you are not losing anything, you are just withstanding your field amplitude. But now if your G is greater than G threshold, that means your E1 will be must be greater than E naught. So, when E1 must be greater than E naught, what happens, that additional field whatever will come here, that will give you some more energy, that overcoming the loss, and that overcoming, when it is overcoming the loss, that means it will start growing energy inside the cavity. And when it starts growing the energy inside the cavity, then you see, because that energy growth how much, that depends on your quality factor, gain, etc., and it will come to a steady state for a given G value. It will come to a steady state where internally some energy will be stored, and that fraction of the energy must be coming out, because this mirror is not 100% reflectivity. That fraction of energy coming out, that will be exhibiting as a laser. That is what actually in a very briefly and simplified way I have explained how a laser emission can happen. That is actually explained more detail in any laser physics book, you can go through that, but here I have just discussed considering the mirror and mirror integrated into the waveguide, and you have certain kind of pump. So, that actually represented here. So, this is the loss, here is the loss coefficient, suppose you are considering, okay, when G threshold exactly equal to loss up to here, okay. So, you do not see anything output here, but when this G is greater than G threshold, as I mentioned, for example, if your gain curve with respect to this one, this is this thing, and your loss curve, it is here like this. This is the dashed line is your loss level. We are considering loss is actually frequency independent, but gain is frequency dependent. Then what we see that these frequency, these frequency, this frequency, this frequency, these 5 frequency, it sees gain which is actually overcoming the loss, meaning those 5 frequency will see gain and it will overcome the loss of the cavity, and that can come out as a laser. So, if you just see the spectrum of the laser when G greater than G threshold, you will see all these longitudinal modes. Depending on the gain profile, you see the longitudinal modes will be which will be higher and which will be lower, which will be smaller, and so on. Typically, if you see any Fabry-Perot laser, depending on the length, etc., you can see there will be distinct frequency, there will be distinct frequencies in the laser spectrum. Though we call it laser is a monochromatic light source, but indeed it is not monochromatic. There is a fine features are there, they are separated by longitudinal modes. Normally, if multiple longitudinal modes are there, in the laser emission, they are not good for precision application, communication, etc. So, it is always good to have a laser to oscillate only in one longitudinal mode. When a laser oscillates in one longitudinal mode, that is called single frequency laser. Single frequency laser. How that is possible? Obviously, I have just listed here. I am not going into detail, but I can give you some kind of overview how to get that. So, what I have discussed here, optical gain, actually that is coming through stimulated emission. For example, that thing you can I think within the scope of this course I cannot discuss that in much detail, but stimulated emission, that means actually if you have a one photon and if you have a population inversion, then that one photon will start help emitting another photon of its own property. So, 2 photons will be generated, 2 photons will be again stimulates into 4 will be stimulates again 8 into 16 and so on, it will be cascaded effect will be there, and you can see a gigantic amount of intensity or power of that same frequency in the same direction, and that is called stimulated emission. And this stimulated emission, basically stimulated emission causes optical gain, and normally where from stimulated, how stimulated, when stimulated emission happens, when there is a population inversion. So, this population inversion is also again very well known in laser physics, but I will be discussing here how this population inversion, what it means in a semiconductor laser diode, and that population inversion, how you can create, how you can achieve, and how that population inverse help for a stimulated emission, and that stimulated emission again give rise to result into a optical gain. Okay. That thing is the whatever I discussed, that is the internal physics, internal physics of any laser cavity, how you are designing your waveguide, active material medium, what is the pumping system, all those type of things involves this starting from population inversion to stimulated emission to optical gain. So, I can see that, I can picturize that. First you get a population inversion in a material medium, that will give you stimulated emission, and that will give you basically optical gain. And optical gain, if you have a positive feedback like a mirror like that, and this gain is sufficiently higher than the loss of the cavity, then you get a laser. That is the overall principle of a laser emission. But as I say that in simple Fabry-Pérot cavity you can have a multiple frequencies, but how to achieve single frequency, that actually depends on your cavity design. Cavity design means how you are designing your mirror. Okay. How is your gain curve? Suppose your gain curve is very narrow somehow, okay, then only one longitudinal frequency only it will see the gain. So, that will be actually lasing. Otherwise, indirectly what you can do, this mirror which is giving a positive feedback reflection to all frequencies, you can design this mirror, for example, using a DBR, distributed Bragg reflector, where your reflection happens only with a narrow band, narrow frequency range. So, that narrow frequency range reflection will give you positive feedback, all other frequency that will be passing, so that will not build up. So, in that case you can achieve also single frequency lasers. Okay. So, that much is good enough for this course. I think if you want to know much more details how one can achieve single frequency lasers, so any textbook you can just consult, and it is not so difficult to understand also. Okay. Now, as I mentioned, we will be discussing about semiconductor laser diode working principle. That is actually most important for our photonic integrated circuits, and today whatever photonic integrated circuits we are implementing and commercially available also, the semiconductor laser diodes are basically integrated on chip, or it can be used off chip and board level, etc. So, to understand a semiconductor, to discuss a semiconductor, again it is a huge topic. There are textbooks are available for only for semiconductor lasers, light emitting diode as well as lasers, etc. But here I will be just giving you an overview which is actually which may helpful for you to understand that what are the limitations particularly for photonic integrated circuit applications for integrating different type of lasers, and how one can proceed to improve it, etc. Let us consider semiconductor. If you just see simple band structure of any semiconductor, normally we see that in any textbook, if you see, there is a conduction band, there is a valence band, and conduction band and valence band, it is whenever it is shown like that, you can consider this x axis is just a position. At any position you go, you can see that electron will have certain up to certain band, it is allowed, energy levels are there, band of energies are allowed, that means electrons can occupy that energy, this is energy axis. And then again there is a gap band, stop band, where electrons is not allowed, those energies are not allowed for electrons. And then again you can find another band of energies, and electron can be allowed to occupy those energies, accept those energies. And in this way, any crystallographic structure, any solid state semiconductor, dielectric or whatever, if it is a crystallographic structure is there, because of the periodic arrangement of atoms or molecules, actually gives some kind of periodic potential for electrons, and that periodic potential if you solve using quantum mechanics like a Schrodinger wave equation, etc., and different methods are there, then you can see that electrons actually can accept only certain band of energies, and certain band will not be occupied, that will called stop band. So, valence band is the band particularly for semiconductor, that is the band where at low temperature all energy levels are occupied, and there are immediately afterwards there is a gap, and above that there is another band of solutions you can get, but electrons will not be occupied because there is no excess electrons. So, all the electrons are occupied here somehow, for example. But in this case it is shown that some open circles, if you see that, that means some of the electrons are somehow missing. At room temperature, what happens? Some electrons, they will interact each other and scatter each other, and they can actually jump into the conduction band. They acquire some energy and go to the conduction. Very little bit amount of electrons can be available in the conduction band. That is what we know as a semiconductor. Any semiconductor, if you see, for example, if you see silicon normally your atomic density in a crystal, that would be about 10 to the power 25 per centimeter cube or so, right, 10 to the power 25 or 10 to the power 26, I think 10 to the power 25 per centimeter cube atomic density. But you know, each of this silicon has a 4 valence electrons, right, has 4 valence electrons. Those 4 valence electrons actually contributes occupy all this valence band. Now, it can happen that because of the energy thermal excitation, etc., so those few of them electron can go up. We see that normally at room temperature a silicon crystal, intrinsic silicon crystal, where nothing, no defects, no doping, etc., is there, in the order of 10 to the power 10 centimeter cube per centimeter cube, number of electrons can be available in the conduction band. So, when 10 to the power 10 per centimeter cube electrons are available in the conduction band, some little amount of conductivity in the conduction band. At the same time, the empty spots here, they are called holes, they can be also, they can also allow some valence band electrons to move in, because there is some kind of empty spaces are there, they can actually hop one atom to another atom, some kind of mobility they will get. So, that is the way a semiconductor is actually distinguished from the metal. How? Because here in this case conduction band you will get certain kind of electrons, some number of electrons, and valence band also some number of empty, and some electron has some kind of, if you apply some kind of electric field. So, this empty spots empty points, they can also move. So, that can be carrying some kind of current, and also conduction band electrons also can carry also current. Suppose you have a n carrier electron density in the conduction band, and P is the electron density hole density, so called empty spots density in the valence band. Both n and this holes, so called holes, they contributes to the current conduction. Current conduction means, you know, the J current density is sigma times E, J is the current density. So, this sigma again you can consider that can be corresponding to sigma n, that means electrons in the conduction band and holes in the valence band, and both actually contributes for the current. Okay. So, that is how we can define. But in case of conductor, normally you do not have such situation, you have only highest band, you will see that it is not completely full filled. So, some empty energy levels are there. That is the reason that highest band, that means this conduction band itself, it has some empty spots, like lot of energy levels are free. So, electron, if you apply energy, electron can acquire some energy and can become mobile, and it can have a conductivity, good conductivity. Normally, you have 10 to the power 22 per centimeter cube free electrons in the conduction band. So, that many number of electrons actually contributes for the sigma. So, if it is a conductor, now that in that case only sigma n, that is actually the current density, you can that means conduction current actually contributed by electrons only. So, that is the difference, the semiconductor and conductor. But in case of semiconductor, you can by doping you can actually change this n free electron in the conduction band and or hole in the valence band, and depending on that you can actually enhance the contribution of sigma n or hole together or individually. Okay. So, that way actually we can control the conductivity of a semiconductor. That is why it is very much important, particularly for electronic industry. That I think that is not the thing I am going to discuss. I will be just taking the important aspects what is necessary for this course, for this chapter of this course. Again, one more interesting thing, if you see that here this energy levels, I say that there are allowed energy levels, they are continuous we said, but actually they are not continuous, they are actually fine features, fine lines are there. So, they are spaced, but they are spacing energy levels, their spacings are so close that you can consider like a continuous. And if you see that the number of lines, the energy states available, that can be shown that can be expressed in terms of this one in the conduction band. Cb stands for conduction band, okay, where Ec is the bottom of the conduction band energy level, energy that is actually defining bottom of the conduction level, and Ev is the top of the valence band, here it is shown. So, in the conduction band, if you see that the number of energy states available per unit of energy, suppose you have considered delta E, this is your E, this is Ec, above Ec you are just considering at a certain value of E. At that particular point, what is the number of density, number of energy levels available at E, that actually can be expressed in any solid state physics book, you can find that can be expressed by this one, where this V is the volume of the your substrate, your material you are using. If you remove this volume, that means per unit volume you can normalized density of states, we call it as a density of states. And to Me is the Me star is the effective mass of the electron in the conduction band, and H bar means it is a reduced Planck constant, nothing but H by 2 pi, and E by E minus Ec to square root. So, that means as you increase the energy, your number of energy levels will be increasing. So, for example, if you are considering at E, you are considering E from E to delta E, how many number of energy levels are available to occupy, so that electron can occupy, then you can say that this one 2 pi to m e star h bar square 3 by 2 E minus E c times delta E. So, that means at E per unit increment of energy, the number of allowed energy levels can be computed by this expression E minus E c. That means this will be always a positive value. Similarly, for the valence band, same thing, but you know here it is a hole empty. So, electrons will see different type of situation. So, here we call it effective mass of the electron as a effective mass of the hole, where is the positive charge, that means the missing of the electrons we can consider like a positive charge, and effective mass is m a star. Similar expression, but instead of E minus E c, E v minus E, because here energy, all the allowed energies are less than E v, that is why E v is greater than E. So, we need to have some positive value. So, we get this type of. So, this is the energy levels available. Now, another interesting thing, I think you all know that at a given energy, and for a given temperature, what is the occupation probability? What is the probability of occupancy for an electron? That is actually defined by Fermi-Dirac statistics. So, energy levels available does not mean that energy their electrons is already occupied. That occupation probability actually depends on your temperature, because normally we know at low temperature entire valence band is completely occupied. Now, if I want to see that I am raising the temperature, so then the electrons can go to the conduction band, and any energy levels available they will try to occupy, and that occupation probability actually predicted by the it follows normally Fermi-Dirac distribution, and that expression is this one, where we have defined another additional energy level called Fermi energy level. So, Fermi energy level according to this expression you can consider when E equal to E f, that means F E will be equal to half. So, occupation probability, that is the energy level we define as a reference energy level we define where occupation probability is a half. So, sometimes it is called actually chemical potential, but in semiconductor it is mostly known as a Fermi energy levels. Okay. So, energy levels available, and there how many electrons can be occupied, that also can be expressed. This one, all these are explained very detailed in any of the solid state electronics device book, but I just as I mentioned earlier that this may be helpful for understanding semiconductor laser also. Okay. So, now as I mentioned, suppose if you are considering p type semiconductor. P type semiconductor means you dope something such that doping level you are just considering some atom like aluminum, you are doping in silicon for example. Aluminum is a trivalent metal, right. So, aluminum or maybe you can consider like a so called boron. Let us consider boron. Boron is also trivalent material. So, what happens, the fourth electron, if this boron is actually occupying some of the silicon sites, the fourth electron is looking like boron will be behaving like a silicon, but fourth electron missing fourth electron. You can consider this boron is something like a silicon tetravalent material. Silicon has a 4 valence electron, here 3 electrons. So, those 3 electrons, this third electron defect states created here. Once it creates here, so lot of electron can get little bit of energy, thermal energy, and can occupy these pairs. So, you can get lot of holes created in the valence band, lot of holes will be created in the valence band. meaning electrons are going a little bit up. So, when electrons are going a little bit up, then occupation probability, where actually you supposed to get half occupation probability, that Fermi energy level will pull downward. So, p type semiconductor, you can have lot of holes that can be conductive, but valence band itself, because of the hole, it starts conducting, okay. And you can see that normally here in case of intrinsic semiconductor, I say that some level of 10 to the power 10, for example, in silicon 10 to the power 10 per centimeter cube atoms are electrons are there in the conduction band, but whenever you are doping p type, normally majority of electrons will be just trapped in this defect level. So, in the conduction band you will not see much. So, the n value here, it was n here and it was n p here, number of intrinsic concentration, whole concentration pi. Now, if it is doped like that, this is n, whatever the concentration, and this will be your p. So, we can consider p type means p type doping is there, we can write like this pp and pp. That means n is the concentration of electron for p type doping and pp is the whole concentration for the p type doping. Normally, in this case pp will be much higher than np. Okay. But in this case Ni would be equal to Ni would be equal to Pi. Normally Ni and Pi, that is actually equal to Ni square. But when this, even though this is happening, here you will see that Np and Pp, that also will be equal to Ni square. So, normally this is actually, this can be shown in any using your all the principles or the distributions and energy density, etc. You can show that whatever this situation, whether you dope or not, that the carrier concentration, electron concentration in the conduction band and hole concentration in the valence band, that will be actually equal to Ni square. Normally they are equal, and Np, even though your whole concentration you have increased, simultaneously your electron concentration in the conduction band will be reduced, and such that this thing will be followed. That means total multiplication should be Ni square, that is actually known as law of mass action. Law of mass action in well known in semiconductor devices. Okay. So, this is actually true, this thing actually true as long as the doping level is moderate. So, normally doping level you can go up to say 10 to the power 20 to 10 to the power 21 per centimeter cube, this type of doping concentration we can achieve. Okay. So, normally if you dope more, heavily doped, so what happens, as I mentioned, this defects level, for example, whatever I am considering, if you keep on doping more and more, then this defects level also it will be like a, it will not be like a only one line, it will be like a broadening. So, this defect line also keep on broadening, and then what you see, that will also penetrate inside because of the doping of boron or etc. Those energy states will be penetrated inside into the valence band also. So, in that case you can see originally there were energy states, and now additional doping, that will create additional states inside. That means you may get a multiple solutions in same level, energy level. That type of semiconductor is called degenerate semiconductor. In degenerate semiconductor, this Fermi level can happen, that can push inside the valence band for p type. Okay. In that case, since the energy, additional energy levels penetrated inside the valence band, that is why it is degenerate semiconductor, and that is the reason you will find that this Np and Pp that will not be equal to Ni square in that case. In case of degenerate semiconductor, this law of mass action will violates, because your defect actually that will modify your energy bands, that will create some kind of degenerate energy states within the band. That is why they are called degenerate semiconductor. And I can tell you that if you want to get a semiconductor laser, one of the major condition is that your semiconductors must be heavily doped such that Fermi level can be penetrated deep inside to the valence band or conduction band. I will show for the, this is shown for p type semiconductor. N type semiconductor also identical situation, the Fermi level can push inside the conduction band. So, in that case degenerate semiconductor required, and that situation you will have this type of situation also, law of mass action, it will not follow the law of mass action, and that is actually one of the important requirement for the semiconductor laser. I will be discussing very quickly. Okay. Now, this is N type, similarly N type semiconductor. So, whenever you are doping your N and here you can get P n. Now, in this case again we can say that N n is much greater than P n now, and if it is a moderately doped, then N n and P n should be equal to N I square, but if it is degenerate semiconductor, N n and P n not equal to N I square intrinsic semiconductor. So, these are very basics for semiconductor, and for degenerate semiconductor, which is very important for our laser emission. I will be discussing that. Now, let us see if you are creating a p-n junction, what happens. If it is a p-n junction, just remember that if this is p type semiconductor and this is your n type semiconductor, and suppose you have a material, in one section you are just having a p type semiconductor, another section is n type semiconductor. What happens? So, you see, because this is the same material, one side you are doping with a p type like a boron, and another maybe you are doping like a phosphorus, where pentavalent material is doped, so that lot of electrons are there, Fermi level here. You see, one side Fermi level is lower, another side Fermi level is higher. But you know, in a semiconductor it is a continuous, the as you go as a function of x, you cannot say that the probability, occupation probability for a particular energy states at the n side will be somewhere here E f lower region, and occupation probability half here will be higher. That cannot happen. What happens? The electrons here will try to move towards the p side, and holes will try to move towards the n side. That will continue as long as this Fermi level from the both sides they align. So, in that case, this entire conduction band in the p side and valence band and conduction band valence band this side, they will start bending like that. That is what it is shown here. You see, this is the Fermi level try to align, and this side in the conduction band, this is the n side and this is the p side. P side, if you see, no electrons are there in the conduction band, almost maybe scattered 1 or 2 will be there, and n side there are lot of electrons in the conduction band, but no holes in the valence band in the n side, this vice versa. Fermi level is aligned like that. This is the standard whenever you are fabricating a p-n junction, and if you see at any position, this can be your so called metallurgical junction. So, this type of banding happens because you know that electron when moves this side, then this side you will get some kind of plus immobile atoms will be there, and this side it will be negative sign will be there, because once electron moves this side from this side to this side, then what happens originally, because even though lot of electrons are there in the conduction band, lot of holes are there in the valence band, as a whole any n type material or p type semiconductor material, they are neutral. But what it is happening here, because of the Fermi level alignment, some electron moves, that means certain region you will see that this positive charge is created, this side it will be negative charge will be created, right. So, that negative charge and positive charge will be created, right. So, in that case you will see some kind of electric field like this. So, when electric field is this one, then what they will do, this electric field actually meaning that means the potential energy for the electrons will be different. So, energy band will be like a bend like this thing, any semiconductor device book, these are known. Now, what happens? Light emitting diode. Suppose you have a heavily doped semiconductor p type and n type, that means degenerate semiconductor. So, that Fermi level is more closer to the conduction band in the n side and closer to the valence band in the p side, and you are giving a so called, what you call that, forward bias. You just go back, forward bias, then what happens, you are, this is already electric field is there, and this is whatever the band bending, that is called actually built in potential. Okay. So, energy difference is q times V V. Now, whenever you are giving a something, you are connecting here positive here and negative here, then what happens, then this built-in potential will start reducing, and then what happens, your some electrons can move into the conduction band towards the p side, and holes also moves into the valence band. So, this is the situation where actually you applied some forward bias, and then you generated some kind of additional electrons in the conduction band in the this depletion region, and additional holes in the depletion regions, that is you can create it across the depletion region. That is actually called population inversion. That is somehow you are actually forcing your distribution, not similar to like a Fermi-Dirac distribution. It is something against the normal inversion, normal population of the electrons as a function of energy, and it is somehow we call it as a inversion, population inversion. So, when this population inversion happens, you can imagine that in this region, that lot of electrons are there in the conduction band and lot of holes are there in the valence band, which is actually against the normal population distribution. So, what happens, natural tendency what would be there, these electrons from the conduction band comes back to the valence band and recombine with the hole, and when it recombine with the hole, it loses some energy. That energy will be, can be radiative energy like electromagnetic wave, or photon will be, one photon will be generated, and that is a natural process, spontaneously it can happen. This spontaneously when it is happening, that photon will be there, and that photon can be considered as a if you can have large number of electron and photon recombination happening, large amount of photons will be coming out, and you can see something like a light source. Okay. But one thing is that it is not that you are creating population inversion, and then in the depletion region because of the forward bias, and photon will be coming out. Sometimes normally we will see that in the next lecture I will show that this, it is not always true that if you are just creating, just giving a forward bias, and even if it is a degenerate heavily doped, it cannot be always true that electrons will recombine to the hole and emit a photon. Instead, what will do that these electrons will try to come down to the valence band, but with a different path, non-radiative path. It will lose some energy to the crystal, to the phonons, and it will heat up the material, but no photon. That is happening in certain type of semiconductor like silicon itself, that never happens this type of photon emission. Okay. So, condition for photon emission is you need a direct band gap semiconductor, which is silicon is not a direct band gap semiconductor, and you need heavily doped both p type and n type to make a junction, p-n junction, and you need a forward biasing. Then when electrons and photons recombines, the energy, if you see this separation, that is actually this is EC and this is EV, that means EC minus EV equal to EG, that is called band gap. So, when photon comes out, the photon energy should be around h nu or h cut omega, we can say that h cut omega. So, this photon, it does not mean that electrons coming from the bottom of the conduction band and just recombining at the bottom at the top of the valence band. It can have certain kind of distribution. So, you can have a photon energy with a lot of distribution. This is your lambda or omega, whatever you can consider, this is electroluminescence. So, you will get a spectrum, broad spectrum. So, LED spectrum, even though if you see blue LED or green LED, whatever available today, red LED, but it will have a certain, even though red it is not one wavelength, it will have certain kind of spectrum that has some range you will be getting also emission. Now, what you see that one photon, if it is emitting, for example, you consider a particular point, this is your energy, this is your x at an unit position. At a particular point, you can see that one electron is just recombined to the hole, and a photon can emit, it can go in this direction, it can go in this direction, it can go in this direction. It is a 3-dimensional option, freedom is there. Even though it is showing energy scale, at any point any photon is emitting, it has option to travel in all directions. Okay. But what happens, it can happen, you consider a certain direction it is moving, for example, x direction. While moving, if it sees that one more electron being, because of the dipole oscillation, certain kind of dipole oscillation, that dipole stimulates again another electron to de-excite, and then you can get 2 photons. 2 photons again helps to generate 4 photons. These are actually stimulated emission can happen. But this stimulated emission should not be lost again, whatever emitting the photons, that should not be lost. You should create certain kind of situation so that these photons are not reabsorbed again. They should come out of this material, so that you can get a good light from a light emitting diode. For example, it is shown here, it has been created certain gallium arsenide. Gallium arsenide is a compound semiconductor, you know, gallium from the group 3 and of the periodic table, and arsenic from the group 5 for the periodic table. If you can make a compound semiconductor like this, they are basically direct band gap semiconductor. That means electron, I will just explain what is direct band gap and indirect band gap semiconductor in the next lecture, but for the moment you just understand that gallium arsenide is a direct band gap semiconductor. You have a P plus doping, P plus means heavily doping to get a degenerate semiconductor, N plus doping heavily doped to get a degenerate semiconductor, and then if you give a current injection, that means you are giving a forward bias like this, right. Then your electron hole recombination takes place and you get energy photon output, right. So, this from the output you can get, this can be clipped surface, this is semiconductor clipped surface, but clipped surface, you know, this whenever it is coming you can get certain kind of reflection here, certain kind of reflection here because of the Fresnel reflection. So, you can think some kind of feedback mirror is there. So, ultimately you may get some kind of laser light, whatever I have discussed earlier. But at the same time, when it is propagating in this direction, as I mentioned that photon should not go other direction, even if it is going other direction, that direction should be lost. In a certain direction when it is propagating, it should be accumulated, it should be confined. So, for that purpose what it is done, people demonstrated a double heterojunction semiconductor. What it is done, for example, if you have one side is so called aluminum gallium arsenide and another aluminum gallium arsenide. That means, you know, gallium arsenide, this is gallium arsenide, right. So, what they are doing, the X fraction of gallium is replaced by aluminum. Certain number of gallium atoms are replaced by same number of aluminum atoms. So, in that case, if you make such kind of compound alloy, then you will see that the band gap will go up, e.g. for L gas is greater than e.g. for gallium arsenide. Now, you see this side L gas, this side L gas, this is EC, this is EV, this is your band gap for the L gas, and in between you have gallium arsenide. This is EC for the gallium arsenide, this is EV for the gallium arsenide. And if you make a junction here, you see there is a clear cut step in EC curve, you see clear cut step here. Similarly, this side also you will see gas will be like this, and this type of things is there. So, now in this region if you see, if you are giving a, suppose this side, if you are giving this side p type doping and this side n type doping, and you are giving suppose forward bias, and this side you are connecting here like this negative bias. So, electron can move. So, electron from this gas side n side it moves, and when it comes here it looks like a quantum well, it can stay a little longer, and holes from this side it come here, it goes here, it is all for hole also it sees some kind of quantum well. So, it can stay a little bit longer time, it can accumulate, it gets time, electron gets time to recombine to the hole. So, you are enhancing the photon emission. So, that means you can in the depletion region, active region, you are creating some kind of confinement of for both electrons and holes whenever you are giving forward bias. Okay. Suppose this is x direction, but at the same time one advantageous situation came. What is that? When band gap is reduced for compound semiconductor, their refractive index is normally increases. So, this is the gas side for example, up to here refractive index is lower. This is the gas side, refractive index is lower position, and gallium arsenide size refractive index is higher. You can imagine lower refractive index, higher refractive index, lower refractive index. So, light can also confine here in this region. So, light can confine. So, let me see this one like this, light can confine here like this. So, that means you can maintain this type of structure in a particular direction. So, light can actually confine along that direction, electron hole pair will be there, population inversion will be there, and you can have a guided mode also, even one confinement you can have. So, as it propagates more stimulated emission will happen. So, you get optical gain, and this is the situation it is shown here. This is p type dope gas, n type dope gas, and in between active layer gallium arsenide you can see here, and you are giving a forward bias here, n side is grounded here. So, you can see that your electrons are being injected, holes will be injected from this side, electrons will be injected from this side, and then the combination happens because of this type of quantum well, and then laser intensity. That means this is actually shown as a guided mode. For example, we have shown earlier it is a 1D waveguide, it is shown here. So, light will be confined here and you can get a laser source here, though it is just one dimensional confinement. You can have, we will show that there is a situation. So, technology available today also you can confine the other side also, you can have a core region only active region, all around you can have a aluminum gallium arsenide. So, you can get a 2-dimensional waveguide where you can actually create so called population inversion like this, electron and hole can be also confined because of the forward bias in the active region, and then it can be optical waveguide also. So, as a photon emit, it can propagate in a certain direction and it can amplify, and you can have a mirror, you can get a gain medium, and you can get laser also. Okay. So, for this type of laser, early 1970s, 60s people demonstrated that the emission, because gallium arsenide band gap, whatever the band gap it is emission, that emission actually supports 850 nanometer wavelength, and that was the first efficient laser source demonstrated and operating at room temperature. Okay. And threshold current, this threshold current, if whatever the current is there, if you just divide it into area, then threshold current density we can call it ampere per centimeter, 9 into, that means 900 ampere per centimeter square, very large amount per centimeter square. If you want to have a 1 centimeter by 1 centimeter laser diode, normally not. Okay. So, then you need 900 ampere, it's a huge amount, that type of current you cannot supply really. So, instead of that, what you can do, your device size, device area, this area can be in the order of some 100 micron by 100 micron for example. So, 100 micron by 100 micron, then you can bring it down your threshold current maybe to ampere level. Okay. So, this is the thing, first efficient semiconductor lasers operating at room temperature, available in the market, and that is the reason when fiber optic communication started, the first generation fiber optic communication actually started with the considering wavelength this type of laser 850 nanometer. That is why 850 nanometer wavelength is considered as a first generation communication window. However, later on it has been shifted. As we go for longer wavelength, we can find that fiber optics actually giving better properties. So, also people demonstrated semiconductor laser diode for emitting longer wavelengths, which is actually compatible to fiber optical fiber, low loss optical fiber, etc. So, that is what we can discuss in a couple of slides, and then we can close this lecture today. So, here actually you can see that this is when it is waveguide, we can say that inside the waveguide how you can accommodate gain medium, because so far we have discussed that in the waveguide it is a passive waveguide. Whenever you are having a refractive index, high refractive index, and then you can have a total internal reflection, you can have a modal analysis, orthogonality condition, etc., and you can guide your light and you can interfere them, so on and so on. But if there is a gain, if it is loss, okay, you can consider e to the power minus alpha z, that is the loss, that coming from sigma and so on, conductivity, etc. But if there is a gain, population inversion is there. In that case also we can modify our dielectric constant like this. It can have real part of dielectric constant, imaginary part of dielectric constant. That means your effective index of the guided mode can see real part and imaginary part with g by 2. If you just replace your e to the power this beta, beta means 2 pi lambda times n effective, right. So, this n effective, if it is real part and imaginary part, that imaginary part normally in the effective index can give you your net gain as well as loss. That is how we can represent. I think this is easy to understand. Okay. And here is okay, one thing I mentioned, that you are just giving a this type of device here. It is kind of 2-dimensional confinement waveguide. You see, this is the active region, gallium arsenide. All around you have gallium aluminum arsenide, and top side it is p type doping, and this all around you can see n type doping. And if you give a biasing here, contact from here, so there is some kind of insulating layer is there, and then you can have a bias, you can have a contact and bottom contact, and you can get current, and then light will be flowing this direction and this direction back and forth. This is your mirror side here, this side will be mirror side, and then as I mentioned that you need at least G threshold to overcome the loss inside, mirror loss, waveguide loss, etc., so that you can get a laser emission. So, that is the reason the characteristics, if you see initially as you increase your drive current, initially nothing happens, very slowly some photons will be generated, but that will not be called as a laser, because that is somehow some scattered photon is coming out, you can measure there. But after certain level you see that your emission, light emission is sharply increasing, almost linearly. So, that is actually laser. And if you just normally if you just consider extrapolate this one where it is cutting, that is actually called as a I threshold. I threshold, if you divided by area, then this will be called J threshold. And this I threshold actually is corresponding to the gain per unit length, gain coefficient, whatever you are getting, threshold gain coefficient you can find out. Okay. And also you can see that this is called actually threshold gain, right. So, from here we can say that to get a laser at least your current should be more than 10 milliampere, 15 milliampere or so here. Okay. Now, if you just take a slope here, this one, that means this is a light output, say D laser output by DIL, that actually instead of IL you can think of how much electrical power you are actually consuming. You can consider something like that DPL laser power, DP electrical power, that will be called as a laser efficiency. How much electrical power you are actually consuming and how much light power you are converting. Particularly, you know that a laser is actually is coming out by electrical currents. So, driving electrical current in semiconductor, you are getting laser light, right. So, that is actually we can define efficiency. So, you have to, if you can get eta equal to 1, that is actually you are not really losing anything, whatever power, electrical power you are consuming, with same amount of light power you are getting, that is called laser efficiency. If you want to learn a little more about all these, you can study famous book Photonics for optical communications, written by Yariv and Ye, and you can get more insights on that. And one, I just want to complete one more thing. So far we are talking about the first generation communication window, because gallium arsenide lasers actually emits at 850 nanometer, but as I mentioned that I will be also showing in the next lecture that if you just engineer, if you just make some alloy composition suitably, then you can actually also manufacture semiconductors, compound semiconductor, which can emit, if you fabricate laser diode, of course, it can emit longer wavelength also. For example, gallium aluminum arsenide, if you are just making, then the band gap you are just can control 0.75 micrometer to 0.8 micrometer by controlling x here. X equal to 1 means x equal to 1 means x equal to 0 means it is basically gallium arsenide, x equal to 0 means gallium arsenide. Now, keep on x increasing, that means aluminum you are incorporating, that means band gap will keep on increasing and laser wavelength, if you want to use that as active element. So, you can control the wavelength from 750 nanometer to 818 nanometer. But normally using this things, I have shown there that 850 nanometer first generation communication window